Welcome to today's webinar. We'll give it about a minute or so, and then we'll go ahead and get started. This is an exciting webinar for us. Greg and I were at the NAFEMS conference in Indianapolis last week, our first live conference like that since COVID. So this is a little bit of a continuation for us of that. We presented on this material, so this is a bit of an expansion. And yeah, so it's good to see some of you today that maybe we saw at NAFEMS and others that are just will have a chance to explain what IGA is in general today. Okay. So I am Matt Cederberg. I'm the CEO of Coreform, and today I'm here with Greg Vernon, the Director of Engineering at Coreform. And today we'll be talking to you and explaining more technically about isogeometric analysis and give a brief technical introduction both to IGA, the U-splines technology, and the Flex IGA technology that we've developed to bring the benefits of IGA to you. So the agenda today that we'll be following, just we'll follow directly that. So first introduce what isogeometric analysis is, again, introduce U-splines, and then the Flex IGA, which we also refer to as the flux representation method that we've developed that really can bring the power of IGA to each of you. Throughout the presentation, we have some breaks where feel free to ask questions, type them in throughout the webinar. I'll ask Greg at various intervals so you can ask questions when you have them. So before we get started, also a little bit about Coreform. So we were founded in 2014 to radically accelerate the engineering design process through isogeometric analysis. And we've done that through creating a couple of products, Coreform Cubit, which is our preprocessor, and then Coreform IGA, which is our solver. We are headquartered in Utah, but we have several remote employees around the US and Europe. And also, over the past few years, we've been the fastest growing company on the Inc. 5000 in the computer-aided engineering industry. And we're just excited to be bringing the benefits of isogeometric analysis to you. So with that, I'll turn the time over to Greg and take it away, Greg.
Thanks, Matt. So as Matt said, my name is Greg Vernon, Director of Engineering here at Coreform. Been here for a few years, and even before I joined Coreform, I was involved in doing some research between Coreform and my former employer as I was investigating IGA myself. And so one of the things I found helped me create transformation at my former employer with regards to isogeometric analysis was understanding a little bit more about what IGA was and a little bit of the theory, so I could go off and research some things myself and build confidence. And so I'm hoping that what we do today can kind of bring the same value to you, if that's of interest to you. We're going to be condensing decades worth of research into this webinar, so there's just no way it can be comprehensive, but I hope that it will give at least a good broad overview. So let's start with just introducing the fundamentals of isogeometric analysis. So first, why isogeometric analysis? This is a flow chart from a study from Sandia National Labs in the early 2000s that many of you may have seen before. If you haven't seen it before, if you're an FEA analyst or a simulation analyst, you definitely have felt this, where in your workflow, the simulations actually end up taking a fairly short amount of time in the overall time to your solution, where especially due to the challenges with hex meshing, we spend a lot of our time, or Sandia found that they're spending a lot of their time in these pre-processing stages, specifically around the meshing process. And so almost 70% or over 70% of their time was spent dealing with the mesh. And then, some other time was spent doing the model prep, but it's really all this expense was in the mesh. And it's been thought that maybe today even that's just gotten more expensive. So Isogeometric analysis was started with the goal of trying to drive those mesh-based parts of the workflow that are non-value added, right? The customer doesn't care about the mesh, they just care about the results and the engineering decisions that can be made. IGA wants to drive those parts to zero as much as possible to get the analyst as close to CAD, as close to the design as possible. While we were at the NAFEMS conference, we put together a little overview animation of our solver. So we're just going to play that here. All of the simulations you see in this little video took less than 10 minutes for us to prepare in Coreform Cubit for the IGA simulation. And they're all solids. So we didn't use any beam elements or shell elements in these analyses. They were all essentially just immersed in a background grid. We'll talk more about those details later in the slide. But as you can see, even like that complex lattice structure was meshed essentially instantaneously in a background box. We can also support STL files, so something that might come out of a topology optimization routine or from a 3D scan of a surface. As we mentioned, meshing is this kind of time-consuming process. It's manual. You can see here all the different cuts I'm doing to my geometry in Cubit just to be able to build that mesh. And I had to defeature a lot of the fillets and complex features away. Coreform IGA, we flipped the script a little bit where you can now just say, keep the geometry as is, immerse it in some sort of envelope domain or bounding box, and then run your analysis directly on it. So as you can see, I've still got all the fillets. I've even got the embossing of the NIST name on part of that geometry. Coreform IGA is, as Matt mentioned, is the native implementation at Coreform that we're developing that implements Flex IGA method. And so, we can support these large or excessively large deformations with a few high order elements. We support isotropic plasticity in our current implementation. It's a material model that we have. But as you'll see later, we can really implement any material model that you would use in a traditional finite element code. We have an implicit statics solver in our code. So this case, we're looking at a reactor pressure vessel and trying to detect whether or not at load pressure, whether or not we'd have plastic strain. We also support implicit dynamics. So here, each frame is a time step taken with an implicit midpoint time stepping method. So really large time steps. But also we can run these explicit dynamics analyses as well for cases where maybe it doesn't make sense to take really large time steps. So you can see here like a model of a Taylor impact. Supports contact, both self-contact and surface-to-surface contact. And so as you can see here with this little toy problem. We also support Julia as our user subroutine interface, which makes it a lot easier to write things like a custom user boundary condition or user materials even. And as you saw in that last little part, we support the 3 major platforms, Linux, Windows, and Mac. And really, so our goal is to be able to run these complex analyses on complex parts without having to defeature and spend the time to do that. So anyways, that was our quick, excuse me. That was our quick demo reel from the NAFEMS conference. So for those of you who saw us at NAFEMS, thanks again for taking the time to talk to us. So what I'd like to do now is transition to let's start diving into the technical aspects. So one of the first questions that I want to address is just how is IGA different from FEA? So on the right here, I've got an FEA implementation of a finite element problem and an IGA. The black dots are the degrees of freedom that we solved for in this 1D problem. So they're scaled by their solution, and the basis functions are colored by their global ID. So you can kind of make out that at every increment of 0.1, we have an element. So IGA simply is FEA. The only difference is that we're using smooth high order splines as the shape functions. So we've departed from low order elements, but also from low order non-smooth splines. In fact, every single mesh you've ever built is actually a spline, because a spline is simply a piecewise polynomial. And so even on the top image there, those are all just piecewise polynomials. So IGA has really just leaned into that fact that we now treat all meshes as if they're splines. And that then opens up the doors to the richness of the theory of splines, which is a rich mathematical area. One of the mathematics we use is called Bezier extraction, which essentially generalizes traditional FEA to support these smooth splines that we want to use as our basis functions. So on the left, we have like an isogeometric analysis. We have the geometry in the top, so you can see the control points, in this case of a B-spline. And then on the bottom, we have the basis functions, and the dotted lines represent the elements. And on the right, we have a traditional finite element approach. We're using cubic basis functions here, but they're a traditional C0 approach. And Bezier extraction is what communicates in between these two frames of reference. One thing you'll notice is that the basis functions on the right are Bernstein. They're not the Lagrange polynomials, but the same thing can be done for even Lagrange polynomials as well. And so this Bezier extraction is what allows us, depending on what kind of functionality we want to do in our code, if we want to look at the global structure of the spline, or if we want to look at each individual element for an operation, Bezier extraction allows us to translate between those two views. And so to summarize this section, IGA is this concept that we're trying to get the analyst to running as close to the CAD as possible. And then using high order splines as an enabling technology to do that. And Bezier extraction really is, if you're trying to understand IGA coming brand, kind of fresh into it, really try to find as many papers or as much stuff you can on Bezier extraction. That is the key to understanding what IGA is. And again, it provides that then local element point of view that we use in traditional FEA codes. And so for those of you who have written maybe like a graduate student level code, I'd encourage you to maybe try to add isogeometric analysis through Bezier extraction into your code. So anyways, with that, I've got a little bit of time for questions, I think, if we have some.
Yes, a few questions, Greg. How is IGA different than using P elements versus the standard H elements?
So we're going to get to that, actually, I think in the next section of the slides. It's really about the smoothness between the elements. So it's like having P elements that are smooth. And so you get all the benefits of P elements without some of the challenges with P elements.
And then a question back from the demo video. Besides Julia, is Python also supported for scripting in Coreform IGA?
Not natively in Coreform IGA. However, there is like a PyJulia, I believe, module. So you could write Python and have Julia call it. I think the same goes for like C and Fortran if you wanted to. But we just needed the performance of Julia, and which is why we made that choice. But you can obviously script around Julia. So if you want to like you can script around Coreform IGA. So if you want to do like automation of workflows, you can have Python automate our Cubit platform and then call off Coreform IGA, read in results and stuff like that. So,
okay,
good questions. All right, great. So I'll go ahead and move on then. So a question we oftentimes get, and a question that I frankly had when I started was, linear hexes just work for these nonlinear problems. So why do I need smooth splines? So hopefully we'll answer that in this section. So the first is, just in general, we want to use high order elements if we could, because they converge faster, so they're more efficient. So on the left, we have traditional linear elements. Solution variable in a elastostatics finite element code are the displacements. And so they'll converge in log space here at a rate of p plus 1. So p being 1, they'd converge at a rate of 2. So you can see we're dropping 2 orders of magnitude for each 1 order of magnitude increase in number of elements. You can kind of trade number of elements for degrees of freedom if you wish. But then things like stress, so derived quantities, so strain is the derivative of displacements, and then stress is proportional to strains, converges at a rate of only p. So each derivative, you decrease the rate of convergence. So if you want a problem to converge for displacement, that's not, I mean, you can get it to converge for displacement, but you won't be as converged for, say, like stress, for like a fatigue analysis, or if you're looking at like a work hardening problem. So if we can, and in some cases, you're order of magnitude more elements, and so it's much more expensive to run those sorts of problems. If you run with higher order elements, again, that p+1 convergence, we're now at a rate of 3, so 3/1. And then now our stresses are now converging at the rate we had been converging at for displacements. So fewer elements, fewer degrees of freedom. And with each increased order, we get faster and faster convergence. So we want to open up those high order elements if we can. Another value of having splines and high order splines is that we can efficiently integrate them. So this is some work coming out of Coreform, and one of our developers, who's also a PhD student or PhD candidate, has been working on this function maxima quadrature. If we look at traditional Gauss quadrature, as we increase degree, we get kind of a proliferation of quadrature points that are increasing pretty drastically here. So if we want to get ourselves eventually to like an 8th order element, we're now talking for this 10 element mesh, we have, say, something like 50 quadrature points in our model. And quadrature points are the expense of analysis. But it's actually known that for smooth splines, the Gauss quadrature over-integrates. And so instead, function maxima quadrature, we simply place a quadrature point at each maxima of each basis function. And so now as we increase degree, with each increased degree, we're only adding a single new basis function. And so we only have to add a single new quadrature point. And so you can see now we're exactly integrating, still exactly integrating these basis functions with only 18 quadrature points, where even for the quadratics of a traditional Gauss scheme has more quadrature points. And of course, over-integrating is one of the causes of locking behavior. And so it's so by reducing the amount of quadrature points we have, we can actually address that. Also, splines produce good conditioning. So one of the challenges with high order elements is that you get really accurate results, but then your spectra of your solutions get contaminated with these admissible solutions that don't really look physical, and they kind of add noise to your solver. And so if you have like an iterative method, it can struggle to converge. And that comes from the bases that are only C0. If we add smoothness, smoothness essentially comes through and cleans up kind of that quote unquote bad math that's infecting our systems. And this makes our problems more well conditioned, so that they're easier to solve with like an iterative solver. If you're running explicit dynamics, it increases the stable time step because you don't have all of these high frequency, all this high frequency noise in your solution. So that's why we want smoothness, is for conditioning. So to kind of summarize that little section, again, we want high order elements because they're going to converge quickly to solutions, as well as be more efficient, especially if we want things like stresses and strains in our results. They also permit novel quadrature schemes like function maxima. We have some papers on Greville quadrature that were kind of the forebearers of this function maxima scheme. But they also can reduce this over-integration, which can cause can cause locking, and then leads to kind of custom element formulations that try to reduce locking. And then finally, they can produce those well-conditioned systems that are really efficient for computers to solve. So I can take a break here for a bit and answer any questions, Matt, that we might have.
Yeah, so about the quadrature points, are they exactly at the maximum, or do you shift them around a little bit?
Yeah, the function maxima are exactly at the maximum. For those who are familiar, we pick the maxima for our quadrature points, and then we compute the weights with moment fitting.
Thank you. And then are they computed for a patch or per Bezier element?
Yeah, so these are computed on the patch level, essentially. So they're computed at the global basis function point of view. And that's what allows us, if you look at the picture here, right, the squares here being the quadrature points, but if we were computing them on the patch level, they wouldn't be at the maxima of the global basis functions like this red function here. So that's where we're computing them at.
Then last question, what's the advantage of the maximum point quadrature versus Greville?
The benefit is that for the U-spline technology that we've developed, there's not a native concept of a Greville point. And so we don't really have the Greville abscissa for the U-splines we've created. We've actually even postulated that perhaps the Greville points for even a B-spline are maybe fine, but they might be fine because they're just so close to the function maxima. So we kind of see function maxima as superseding the Greville point work. But yeah, great question. Okay. All right, I'll move on to the next section here. I did see there's a question that comes in that maybe we'll answer at the very end. So U-splines are then a spline technology that we've developed at Coreform, which we believe addresses a lot of the issues that were outstanding with traditional splines that make them now really suitable and desirable for analysis. So there's been a need for an unstructured spline because if you look at the traditional B-splines, they're limited to uniform degree because of the, they were defined through, Cox-de Boer recursion or Castigliano's algorithms that made assumptions that they were going to be uniform degree. But then if you wanted to build like a two-dimensional or a three-dimensional basis, you couldn't use like Cox-de Boer recursion to build those. You had to switch to a different algorithm, which is essentially to take tensor products of univariate splines or spline bases to then construct this, say, this one basis function here in purple. But then also, if we say build a mesh that's unstructured, that tensor product is inherently a structured layout. It has, U and V principal directions. And so we could really only build smoothness over a single NURBS patch or B-spline patch, which I've colored here in gray. Some cases, right, I just ran out of colors. And so you might, some of them don't maybe look exactly rectangular, but they're all rectangular patches. And at every interface between the colors, we would lose smoothness. They're going to be C0, and we lose that desirable smoothness property that we want to have. So we want a spline technology that's able to take this unstructured layout and build maximal smoothness into our basis if we can. And that's what we wanted to address with U-splines. So U-splines are then a novel spline construction technique where all we need for the input is for you to define, what's my mesh and what are the local spline properties that I want. So I want like, a spline that maybe has 3 elements that are quadratic, cubic, and quartic with maximal smoothness between them. And then the output of the U-spline algorithm is a spline basis, as well as the control points that fit like a geometry that satisfy our request. And this then enables maximally smooth basis. And it really, in many ways, is a fulfillment of that original vision of what B-splines were supposed to be, where the B stood for basis. I want to build a basis spline over some spline space. But we were restricted in the spline spaces that we could use, and now U-splines have opened the door. They also offer novel analysis features such as, again, non-uniform topology. We're going to talk a little bit about the top left square here, this refinement, but also, triangles as well, non-uniform degree and non-uniform degree with the non-uniform topology, as well as the non-uniform smoothness. And so it's kind of a maximum flexibility in what we can design for our spline space. But also the U-spline algorithm extends to higher dimensions. So we don't have to do one algorithm for 1D and then switch to go to 2D or 3D. We can use the exact same algorithm, just requested on different dimensionalities. And so these both here are maximally smooth U-splines on the volumes. And then also, we started off when we were designing U-splines or developing U-splines that we wanted them to have all the properties that made them suitable for analysis. And so we can also then use these U-spline elements that are volumetric in this finite element analysis here, or an isogeometric analysis, because again, those are kind of equivalent thoughts. One of the things that you'll see a lot of, so that previous slide we showed like a refinement. A refinement that we make heavy use out of in Coreform IGA is what's called hierarchical refinement. And what that essentially is, if you look at a basis function, there's a hierarchy of levels where you can represent that basis function as a subdivision of basis functions of the same polynomial degree. So this is a quadratic B-spline basis function, and then there are these hierarchical subdivisions with other quadratic B-spline basis functions. And what we do then, that's what, there's a lot of folks who are doing hierarchical refinement with, say, B-splines and other sorts of splines, but we build essentially 3 levels of our basis: a coarse level, maybe a medium level density and a fine level density. And we can go, a 4th level, a 5th level, however many you want. And then where you want to have refinement, we then are replacing those basis functions within those higher levels of hierarchy refinement. But all of these levels have kind of like existed when we built or defined our U-spline space. And this allows us to then turn on or turn off these basis functions. So while these are with B-splines, we can do the same thing with U-splines. And so then what that can lead to, again, is just this mesh, right? We've got these multiple levels of this mesh here. So you can see if you really wanted to refine in this region, you could do that. And then just the proof that, so this is an unstructured spline. This is a U-spline here. You can see where the lack of structure or where the unstructured comes in. And then we've refined 2 levels down to be able to resolve the maximum principal stress here on this plate with the hole problem. You'll notice that this is not using the function maxima quadrature here. So these are just standard Gauss quadrature points. So to summarize, U-splines are a really powerful spline technology. They provide all of these different things that we've been talking about, from like the high order elements. We want smoothness. We want to be able to refine our spline space, design kind of custom spline spaces. But also we want it to be compatible with the traditional fine element approach. We've defined U-splines really in a Bezier extraction framework in many ways. And all of this and a lot of more properties are all available in that single U-spline algorithm. And so in our opinion, U-splines have really enabled then these robust, high accuracy and efficient simulations within the traditional IGA workflow. So with that, I'll take a little bit here to maybe answer some questions if we've got them.
Yeah, so one question is, with the smoothness available with U-splines, can they also model discontinuities?
Yeah, that's a great question. So the answer is yes, in that they can model discontinuities as well as any fine element code that's C0 bases can also model discontinuities. Again, we can switch ourselves down to a Bezier extraction kind of framework. And if the discontinuity is, say, like a crack opening, we can do all the same things you would do with a traditional finite element. But also, because they're high order, even if you're, say, talking like a sharp transition in your solution space, the high order nature is what allows us to then recover those kind of sharp transitions, especially when coupled with local refinement. And so for things like, highly plastic problems, we've shown that they're able to do that.
Great. Thanks. There's other questions, but I'm going to save them to
Sure.
the end.
Okay. All right. So now let's talk about, though, I showed that tensile bar, but that's a body fit mesh. I had to take time to mesh that. Let's talk about how do we achieve this IGA vision we started off with, which is really the model preparation problem. So there is still a remaining challenge, which is hexahedral meshing. So on the right here is a U-spline. It's a hex mesh. It's a body fit hex mesh without defeaturing this piston geometry at all, right? So if we want to do analysis exactly on the initial or on the exact same CAD geometry, what we've shown so far, you'd still have this huge effort in trying to build your hex mesh. And so why hexes? Well, tetrahedra in the general case require a degree 9 basis before we even achieve smoothness, so C1 continuity. And so it's just too expensive to be able to use tetrahedra, and we don't get all the properties about having a maximally smooth basis. So we have to do hexahedral meshing as kind of core to IGA. And again, that is the problem that we were trying to fix in the first place. And so we haven't really addressed that problem. Yes, we can do more accurate simulations more robustly, but we haven't really achieved the vision of IGA. So there's a method that you may have heard of called the finite cell method, which is really starting to respond to that issue. And so it kind of, you take a geometry and you immerse it in what we call an envelope domain. And that now is a trivial to mesh volume. And it's this embedded domain method, you hear them called immersed. And a lot of the finite cell approaches have demonstrated or utilized high order finite elements, sometimes B-spline elements with hierarchical refinement. They've used adaptive integration at surface boundaries, and they've used weak enforcement of those immersed Dirichlet boundary conditions. And so this really has achieved the vision of IGA in that you now don't have to spend any time meshing if you don't want, which is really what the whole purpose was. But there are some limitations. So one of the limitations is that finite cell uses an affine mapping for that background mesh, which really limits us to only being able to use these bounding box approaches. And for the most part, we've really only seen B-splines being used or other structured splines. Even T-splines, they have a lot of structure in what they're able to do, and they have maybe some limitations. So we kind of limited to those kinds of bases. And maybe for a variety of different reasons, they tend to be very computationally expensive because of that bounding box approach, and maybe put a little bit more effort on the computers, and maybe just can't solve certain kinds of problems. So it's at least appeared that from a commercial implementation standpoint, that most implementations of the finite cell method do seem to be limited to linear or small nonlinear, like barely nonlinear problems, and mostly seem to be for design guidance sorts of analyses. So at Coreform, we want to solve the most challenging nonlinear problems that are out there in the industry that kind of require the most effort in trying to prepare these models because they're mission critical. And so to do that, we've developed what we call the Flex representation method, which is the technology behind them, what we call Flex IGA, which is the application of Flex representation method, which we'll also call FRM. So at a high level here, we now contrast to the finite cell approach that we showed. Really what it is we've married finite cell method and U-splines together into a single technology. And what that means is that because we can have unstructured meshes, we can now conform, if we wish, parts of our envelope domain to the body, maybe in a critical region where we want to really converge really rapidly to a solution. If it's like a mission critical feature. And then we inherit all that accuracy and like local adaptivity, P refinement, hierarchical refinement that we got from U-splines. So here you can see is again this little jelly bean. You can see that there's to be able to fit this with a quality mesh, we have a single extraordinary point. So that's where the unstructuredness comes in our model. But then we're maximally smooth in our U-spline space. And then we've done hierarchical refinement around these edges. Now, the refinement done here is just what we have available today in our qubit code, which doesn't actually do all of the local refinement we could have done. So there's actually more refinement here than was actually needed. But this is what's achievable today in our qubit software with the logic that we've built into it. I guess I should mention, so then our boundary conditions can either span from being fully immersed or conforming to the surface, or they can even kind of go across where they're both immersed and conforming. And so really what we see this as that is that open up a spectrum of different workflows that an analyst can choose to use. Anywhere from a traditional FEA workflow where you're likely defeaturing your model, so maybe removing some fillets that we'll see later, to build a body fit hex mesh, or the finite cell approach, which is just immerse the whole thing in a bounding box. We've now kind of filled in the gaps between where by having a little bit of body fitting, you can actually improve the conditioning of your systems, decrease degrees of freedom required to get accurate answers. And it may only require a little bit more prep time. So what you might do is on parts of your model you don't really care about because they're not critical to the results, there's maybe part of an assembly, you can go ahead and immerse all of those essentially instantaneously. And then maybe on some parts that you care more about, you can maybe spend a little bit of time to only immerse the things that are challenging to mesh. And so in this case, it's second here from the left, everything is body fit. The one challenging part were these shoulder fillets. And so what we've just done is we've just immersed those regions. And now this is essentially, it's still really easy to mesh. It takes 5 minutes to mesh this part once you have this kind of this immersing region here. And so this is likely to get you rapid convergence to properties that you care about maybe in this region. So a little bit of how FRM works. We've got a theory manual that we'll be publishing soon. We're just working on some technical challenges with hosting it and a little bit of editorial cleanups. But at a high level, what we've done is that the geometry, as opposed to the mesh elements in conforming to the boundary and then the boundaries of the mesh elements defining where the geometry is, we are capturing the geometry in the U-spline basis. So here, like this point here, we represented in our bases as at some parameter value. And then through the analysis, we're tracking the deformations that are being applied at that location. And that's how we are tracking like the surface. And then within these elements, we need to refine, we need to be able to make sure we're integrating up to these boundaries really accurately. So we use then various different methods. It's like we have like octree and octree plus flex, or sorry, plus function maxima. We have a variety of different techniques to then integrate the basis functions that are cut highly accurately. In addition to the actual hierarchical refinement of the basis functions. So if you're interested, we do have, again, hundreds of pages of theory that we'll be publishing shortly. And so stay tuned to Coreform just for when those are released. And so just to summarize FRM, we removed that constraint that the mesh must conform to the geometry, which is really what the challenge is behind the hex meshing problem. And so by relaxing that, we've now minimized the effort required. We're representing the geometry in the spline basis. And it is the enabling technology that, or the enabling technology for FRM is, again, those U-splines, where we have the high accuracy per degree of freedom, local additivity, great conditioning, efficient quadrature schemes, and able to choose an unstructured mesh. So in this example here, again, another kind of similar to the jelly bean we showed it previously, we were able to get a high quality mesh by having a single extraordinary point, which is a bit hard to see now that we've done this hierarchical refinement. But it's that unstructured nature, which is what allows us to be able to build this partially body fit mesh, where we've immersed just the interior features on this shell. Maybe I'll pause here, Matt, for a few questions if there are any.
Yeah, there's a bunch. Maybe let's ask a couple. We can finish up and ask the rest of them.
Okay.
So the question earlier, and I think maybe you've answered this since then, about whether the hex meshes that we use for FRM work with hanging nodes.
Yeah, so hanging nodes is what people would, it's kind of the colloquialism for like a node that's here at this T-junction. But the difference is that a hanging node essentially means it's not supported in the basis, and so you might have to use like a tie constraint between them. And that tie constraint might happen automatically, or it might be something that you as a user would specify in your prep. These nodes are fully supported in the basis. So they have the properties of the smoothness. So they're not truly hanging. They're just we have a kind of a term for, we call them like super smooth intersections. But they are fully supported in the basis. So they look like a hanging node, but they're actually not a hanging node.
Great. A couple other questions. How does the FRM differ from phase field or layering approaches?
Yeah, so in the layering approach, right, you're moving things through the background grid, but the background grid doesn't really change. Everything's a state variable. In this case, we're still a Lagrangian formulation. And then phase field is in a partial difference equation you're solving in your basis. And so we've actually used U-splines before to do phase field analysis for like fracture. We haven't yet done that with FRM, but we can solve those same sorts of problems with this. Again, it's just we're solving a different set of equations in this.
Okay. And then one more question for now. T-splines also allow local refinement of geometry. How does U-spline technology differ from T-splines in terms of local refinement?
Yeah. So Matt, you may be one of the experts on T-spline on the call today, but T-splines essentially, they were designed, or the T-splines were developed for design purposes, specifically to try to build smoother surfaces for, say, like automotive body styling. They actually have some limitations on what degrees you can have for the T-splines and have smoothness, but also there's limitations on, you thought you might be able to refine locally, but there's actually local dependence that could occur through these hanging nodes kind of interacting with each other, which didn't really allow for the true local additivity that we wanted to achieve. And so there's a variety of other issues, but we looked at T-splines as kind of the foundation for, okay, well, what if we try to do all the things we did with T-splines, where we're designing them to be suitable for CAD design and for analysis. And so that's really what U-splines are. It's kind of just a rethinking of what a spline should be, or what properties we want to solve with the spline.
Yeah, I'd agree. A lot of the creation of U-splines was motivated from what we learned from T-splines. So,
yep.
Okay, great. Go on.
Yeah. So now I'll just put this all together now in an example in Coreform IGA. So if we have this C-frame here on the far left, this is a geometry that came from the designer. There are some fillets for stress relief, but also from a hazard standpoint, the CAD designer's gone in and put a fillet of a minimum radius, so there's no sharp edges, so that in the US there's an organization called OSHA that specifies that you can't have these sharp edges that could cut someone. So they put those fillets in, and that's now in your design model. Clearly, I don't want to mesh those. If I care about whether or not, if I load this, am I going to fail at the inner of this bend? So I would defeature those away. But again, that's part of like that workflow cost that we pay. So we just immerse this in an object domain that kind of captures the major features of this geometry, but immerses all of these fine details, which is then a very rapid process, and it's not challenging to build a hex mesh on this at all. And then we can compare this to then traditional finite elements that are based, we're basing this on traditional nonlinear analyses that use linear hexes. And if you look at the convergence to our solution with cubic U-splines, we've essentially converged to the solution in about a bit under 10,000 elements. And we're honestly really close, even around only 1,000 elements. Whereas traditional linear elements, we haven't even converged to a solution at 1 million elements. And this is one of the reasons why techniques like Richardson extrapolation are popular for verification, to extrapolate out, well, what's the solution that I was shooting for or targeting, which might be up at like 10 million, if I had 10 million elements or 100 million elements. And that's even for a simple problem. And so we can see that you can kind of make out that we're converging towards the same solution, but we've done it much more efficiently with high order U-splines and the Flex IGA approach. So to summarize the webinar today, it really is time for the next generation of simulation. We at Coreform believe that FRM is that next generation, and it accomplishes this by, again, leveraging all the unique computational advantages of smooth splines through our U-spline technology that address all the different limitations and bottlenecks that we've had in our traditional simulation workflows. And so we encourage you to reach out to Coreform to discuss how Coreform IGA can maybe solve your tough, challenging, intractable engineering problems. And with that, I guess that's all the content I had today. I'll open up to questions at the end.
Yeah. Greg, thanks again for the preparation and sharing of that webinar. We do have a number of questions, and I'll kind of start reading through them. From Arthur, wouldn't higher order elements lead to much denser stiffness matrices?
So they do result in stiffer in denser stiffness matrices. Let me see here if I've got, but the difference is that those stiffness matrices are then much smaller. So for instance, here I can maybe, I've got some specific examples in some backup slides, but I think I can talk to it here. If we look at the quadrature slide again, if we look at this, I have only 18 basis functions in this 10 element analysis. Whereas if I was using traditional C0 elements, I'd have, so these are degree 8, so there's 9 basis functions per element. So 9 times 10 would be 90. I'd have, and then subtract away, I guess, the interfaces. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 81 basis functions if I was traditional C0 elements. And so, but that stiffness matrix that would be, on the order of 81 by 81, there's obviously material models that would, will make it bigger, but that's really the scaling, is this 81 by 81 system. Yes, it will be sparse or sparser than the smooth splines, but it's also 81 by 81. Whereas here we're dealing with an 18 by 18. And so it's so much drastically smaller. They still do tend to be sparse in the, in the technical sense, or, less than 10% sparse or 10% dense or 5% dense, but they're just much more compact or smaller systems. So it really doesn't matter that they end up being a little bit more dense. So hopefully that helps answer the question.
Yeah, great, thank you. So here's another question. What are the system requirements for a comparable finite element analysis? For instance, do you have some estimates about how much faster the solution with IGA is computed compared to a finite element analysis with the same level of accuracy?
Yeah, so there's a couple answers to that. One is that in terms of like actual implementation today in Coreform IGA, that there is a significant difference in the performance, but from a practicality standpoint, between what you might see in a traditional FEA code and Coreform IGA, largely because Coreform IGA is just a really young code. But when you look at it, when you look at these things, like if I can drastically reduce the amount of quadrature points I would have compared to traditional FEA, I still get linear systems of equations that come out. Those linear systems of equations are smaller. Yes, they're more dense, but they're smaller, and they have better conditioning. So whereas traditional methods, as you increase degree, the condition number increases. In our case, the condition number decreases. Or if it increases, only increases like by little bits as opposed to like doubling. Those things now allow you to, say, efficiently use iterative solvers as opposed to direct solvers on the linear equations. So all these things are kind of being pieced together, where we're seeing that we can actually be much more computationally efficient than traditional approaches or traditional FEA. However, there are no benchmarks that we can provide you today that literally show that in execution of the code. But we see those things when we look at something like this C-frame analysis, that when we look at the linear systems of equations for each of these kind of setups, like they're just much more well conditioned. Because we're able to converge with fewer elements, that means we have, not only are we smooth elements that are high order, but we're also many times fewer degrees of freedom. And so all those things kind of come together to say that for the same level of accuracy, that I think we will be very competitive from a performance standpoint. And there have been some problems that some of our customers have been unable to solve on HPC systems with thousands of cores that we've been able to solve on like a laptop, because of that really good conditioning of the problems that smooth splines give us.
Great, thanks. Along this slide, Petter had a comment or question about whether it'd be more accurate to be graphing comparing the degrees of freedom instead of the number of elements on this slide.
Yep. Yeah, so it would be. The reason why we show number of elements is mostly just pedagogy, that we figure that most people still kind of think in an element kind of standpoint or an element point of view. What I can say is I can share out the degree of freedom slide or picture as well. It essentially looks the exact same. Just the numbers on the scale on the bottom are different, and there's like a little bit of a shifting. But you see essentially the same behavior, that they're almost indistinguishable. If I were to remove number of elements and number of degrees of freedom from the two images, you wouldn't be able to tell which one was which, because they tell the same story.
Great.
But that is a really great point. We should be looking at degrees of freedom as a way for us to talk. Yep.
Okay, thanks. Another question, when can we expect the rollout of the Coreform IGA software? Maybe I'll go ahead and answer that one.
Yeah.
So Coreform IGA is available now. And if you would like to use it, then reach out to us. We'd love to talk with you and get you in that. Similar question, can academic researchers utilize U-splines in their work? And if yes, how? So this is also an ambition that we have. So just disclosure, both U-splines and the FRM are patent pending technologies, but we're very eager to make them available for exposure to academic rigor and critique and further research. We think it's an extremely rich research venue. And so we have ambitions to make, so first of all, U-splines are available actually in Coreform Cubit. So we have free licenses of Coreform Cubit available for anyone for non-commercial use. So you can access U-splines there. And Greg's just pulling up the documentation about how you can actually build U-splines in Coreform Cubit. If you're interested in researching U-splines, there's a number of research efforts underway, and feel free to reach out to us and we can figure out how we can collaborate with you.
Yep. Yeah, and along those lines too, so Coreform Cubit is then able to export out the Bezier extraction data in a BXT file. We also are working on kind of the next version of BXT formats in a JSON format. And so, yeah, from a researcher standpoint, the Coreform Cubit is the way to be able to start using U-splines in your research.
Mm-hmm. And similar question, is it possible to develop plugins for Coreform? I assume it means Coreform Cubit. Yeah, there is we have an existing API that's in, let's see. Well, I guess the existing API is in C++ and the Qt GUI. We're adding JavaScript and Python support as well. So yeah, if that's something you're interested in, we would be very eager to discuss that with you. Another question, since FCM uses adaptive integration to capture the physical domain, does this raise particular efficiency issues due to the huge amounts of integration points?
Yeah, that's a great question. So it does raise efficiency concerns. You do run the risk of having just a blow up of quadrature points, and that's so there's been a couple of ways we've resolved that. Again, one is this function maxima quadrature scheme is our answer to that. And so when our documentation, when our theories kind of been published, or theory manuals have been published, you can read about that there. But that's what then allows us to then get away with many times fewer elements. But you still need to say, like, predict the weights. And to do that, you have to have an accurate integration, at least at the start, to be able to predict quadrature weights. And so we've actually there's some theory that you can find out there on folded quadrature, which allows us to then even efficiently compute those integrals for then our function maxima schemes. So that has been a core challenge at Coreform, has been that, and we think we've addressed that with function maxima, our function maxima scheme. Yeah, that's a very insightful question.
How would one go about quantifying the numerical uncertainty due to convergence within IGA?
So I'm not exactly sure what's being asked there. One can be that, so if you have like condition numbers, the order of your condition number kind of tells you in some sense how many decimal places starting at like the most significant or the least significant, I guess, so all the way down, so 1.00001. It tells you how many of those digits can you not really trust in your final solution. So if you have a condition number of 1e16, that's effectively a singular system on a 64-bit computer. And so having condition numbers like 1E4 means you essentially have 12 digits of accuracy. So 16 minus 4 would be 12. And so that's one way you can kind of quantify some of the uncertainty in like your solution. But it also means that like if you're doing a Newton-Raphson and you're trying to do searches for like next directions, you also have a lot of accuracy in being able to predict like the next directions for your solvers to go. There has been some work, if the question is instead more around like including stochastic uncertainty, there has been some work in spline-based finite element analyses in general for that. But we haven't searched too far into that at Coreform with our FRM. And then alternatively, if instead the question is now we're going to solve these with iterative solvers, and now I've only solved something like 1e minus 3 or 1e minus 5, is that uncertain or not? And I guess my answer there is that in many cases we don't even know our material properties to an accuracy of 1e minus 5 from a relative or scientific accuracy standpoint. And so getting good enough solutions is kind of the key in engineering, that we don't necessarily need to drive all of our solutions to an accuracy of 1e minus 12. It's just overkill in many of the real engineering problems. So hopefully that shotgun approach to my response answers those.
Cool. Great. Thanks, Greg. So maybe come for a couple more questions. How well does this method work with, how easy is it to parallelize?
Yeah, that's another great question. So we've been focused on, for now, getting things to work, but we've always had this, we've known that we have to be able to run in parallel. So we've actually been working with a couple national laboratories who are involved with exascale computing to integrate some of the technologies from some of their open source libraries into Coreform IGA. So you may have heard of, there's MFEM is one library in particular that we're investigating right now, but also our solvers are all based on PETSI. And so PETSI is providing us essentially with massively parallel solutions, linear equation solutions. And then MFEM we're investigating to marry with our function maxima to then do really rapid assembly. So yeah, parallelism is definitely something we've been working on. It's our goal that we could run on anything from a laptop, maybe even a smartphone if we can nail it and the smartphones get faster, all the way up to the largest supercomputers in the world. And so we want to be able to have that flexibility run on all of those.
Okay, great. So again, Greg, thank you for presenting this. Thanks everyone for attending. This was an unusual webinar for us in that it was so technical, not as focused on applications. We did this because our culture at Coreform is very technical, and this is what excites us, and we're eager to share. So those of you that were able to stay with us this long, and perhaps this is interesting to you, I guess a couple of actions here. One, if you're in industry, we would love to engage with you and kind of prove out.
Matt, I think we lost you, perhaps.
We're eager to explore how we could collaborate with you. And then also, we're always hiring at Coreform. So if this looks like something that you would like to get involved with more intimately, reach out. We'd love to have a conversation. We are fully remote, so we have employees all over the country.
Yep.
And
and Matt, there is one last question that Peter has brought up, requesting if could we get questions answered by email? And I think the answer is yes. I think we'll also try to. There are a lot of great questions that were asked during this webinar. I think we'll try to also provide responses to even those questions, even ones that have answered. We'll verify our responses and we'll post them probably on our forum, I would imagine, or in a follow-up email.
Yeah, I think that would be the best place to drive further questions is to our, I don't know if you just spot to pull it up, Greg, the forum.coreform.com.
Yep. Yeah, so if you go to forum.coreform.com, there's a Coreform IGA section. If you ask your questions here, we see those essentially instantaneously. They get posted to our Slack channel internally. but then also that other people can then benefit from your questions. So I would encourage you to use the forum. But if you have proprietary questions, you certainly can email your proprietary questions to us.
Great. Thanks again, everyone, and enjoy the rest of your day.